sklearnmetricsaverageprecisionscore. Average precision score. Description. The average precision AP score is a metric for evaluating the performance of a binary classification model, particularly when dealing with imbalanced datasets. It assesses the model's ability to rank positive instances higher than negative ones. AP is particularly useful when there is a high-class imbalance, as it is less sensitive to the number of false positives than other metrics like accuracy. Inputs. Why true? The true labels of the data points. This should be a one-dimensional array or list containing binary values 0 or 1 representing the actual class labels for each data point. Y scores the predicted scores or probabilities of the model for each data point. It should be a one-dimensional array or list representing the model's confidence that each data point belongs to the positive class. Outputs. Average precision. The average precision score, a value between 0 and 1, indicating the model's performance. A higher value signifies better performance. Steps. Precision recall curve calculation. The function first calculates the precision recall curve for the given true labels y true and predicted scores y scores. The precision recall curve shows the trade-off between precision and recall at different classification thresholds. Area under curve AUC calculation. The average precision is then computed as the area under the precision recall curve AUC. The AUC represents the overall performance of the model across different thresholds. Metrics. Precision measures the proportion of correctly predicted positive instances among all instances predicted as positive. Recall measures the proportion of correctly predicted positive instances among all actual positive instances. Visualization plots. Precision recall curve. A plot showing the relationship between precision and recall at different thresholds. This plot helps visualize how the model's performance changes as the threshold for classifying an instance as positive varies. Fine-tune parameters. POSLabel specifies the label of the positive class. By default, it's assumed to be 1. You can change this if your data uses a different value for the positive class. Average determines how the average precision is computed if multiple classes are present. It can be set to micro, macro, weighted, or none. Uncertainty methods. Confidence intervals. Estimating confidence intervals for the average precision score can help assess the uncertainty in the model's performance. You can use bootstrap resampling or other methods for this purpose. Sensitivity analysis. Examining the impact of changing the threshold on the average precision score can help understand the robustness of the model. Challenges and fixes. Challenge 1. Imbalance in the dataset. Highly imbalanced datasets can lead to misleading average precision scores. If there are significantly more negative than positive examples, the model might achieve a high AP score by simply predicting most examples as negative, even if it fails to correctly identify many positive instances. Sample use case. A dataset where 99 of examples are negative and only 1 are positive. Fixes to challenge 1. Oversampling. Increasing the number of positive examples to balance the dataset. Undersampling. Reducing the number of negative examples to create a more balanced dataset. Cost-sensitive learning. Assigning different costs to misclassification errors based on the class. Imbalance. Challenge 2. Low recall. A low recall score can indicate that the model is not identifying a significant proportion of the actual positive instances, which can be a problem in applications where accurately identifying all positive instances is crucial. Sample use case. A fraud detection system that fails to detect many fraudulent transactions. Fixes to challenge 2. Adjusting thresholds. Lowering the classification threshold can increase recall but potentially decrease precision. Feature engineering. Exploring and incorporating new features that are more discriminative for identifying positive instances. Model tuning. Experimenting with different models and hyperparameter settings to find a model that achieves a good balance between precision and recall.